I have the pleasure and also the honor to present our keynote speaker, Andreas Zeller. So let me just give a brief bio of Andreas. So Andreas Zeller is a faculty at the CISPA Helmholtz Center for Information Security, as well as a professor for software engineering at Saarland University in Saarbrücken, Germany. And he has done a lot of highly influential research on automated debugging, mining software archive, specification mining, and security testing. And personally, I've been impacted by a lot of Professor Zeller's work. And Professor Zellers is also an ACM Fellow, an IFIP Fellow, an ERC Advanced Grant Awardee, and also he holds an ACM SIGSOFT Outstanding Research Award. So without further delay, let me present Andreas, who's gonna give us this keynote on user interface grammars. Andreas, please.
So, hello everyone. So, good morning, good evening, good night, wherever you are, in particular for those of you on the other side of the globe, for which it is now in the middle of the night. I'll be happy to share my slides. Let's see whether this now works. So here we go. You should now be able to actually see the window with my slide. Am I correct? David, do you see something?
Yes, I can see your slides.
That's so great. Wonderful. Now if I find a way to also see you folks. Ah, yeah. Okay, great. Wonderful. Yeah. Oof. So if you turn your video on, I'll be able to see you and your reactions, and then I'll be able to adequately respond to it. So if you are smiling, then I'll continue as planned. If you're sleeping, then I will speed up. And if you are super excited and everything, or if you just look puzzled, then I'm going to slow down. So your visual feedback is highly appreciated. Of course, if you just take your whatever static picture looking in excitement all the time, I will just take that and everything will be great. So today's talk is about user interface grammars. And just in case you're offset by the word grammar in there, and if grammar reminds you of formal languages 101 or theoretical computer science 101, and reminds you why you eventually went into software engineering rather than into theoretical computer science, don't worry so much. It's not so much about theory, it's actually all about application of things, yet with a bit of a formal foundation. And this idea of a formal foundation is actually the subject of my talk. What I'm presenting in here is means to separate what we normally take in what we normally do in our tools, to modularize this, to come up with a sound formal model on which we can base later things, and where we can can you actually see my mouse pointer in here? Just checking. David, do you see something?
Yes.
Yes, you can see it. Oh, that's great, wonderful. And where we start with user interfaces, where we extract models with a solid formal foundations, which we can then turn into parsers and producers, and on which we can build testing and exploration strategies. And all of these being independent from each other, that is, we can reason about strategies without having to reinvent our own productions, our own models, and our own user interfaces up front. So this is what this talk is about. Thank you very much. Thank you very much, David, for having me here. But now let's actually get into the topic. So first part is about generating inputs. And generating inputs is, well, not really new. We have had this now for some 30 years or so, even longer if you look at software engineering. In security, we have the field of fuzzing, where the whole point is to generate plenty of random inputs for a program and then have this program happily crash. And since generating random inputs is not very complicated, actually it takes about 5 lines of code to produce them. So far for impactful research, actually the biggest, the fewer lines of code your program has, the greater the chance of it actually having a big impact. And this is super simple, and there you go. You create random inputs and feed them into your program of your choice, and then it crashes. Unfortunately, if you just do this for a somewhat more complex interpreter, say something that actually accepts arithmetic inputs, and you go and actually feed, well, random characters into it, even if they come from a limited character set, you will find that the interpreter is actually going to simply reject these because these are syntactically invalid. So what you need in order to get deeper into your interpreter of sorts is something that actually gives you valid inputs, and a means to characterize these valid set of inputs is by using a formal language model, for instance, a grammar. And this is what you see here is a grammar for arithmetic expressions. This is sort of the poster child for grammars. So grammar specifies a language, a set of inputs, and we have expansion rules in here. We start with a start symbol, which becomes an expression. An expression has various forms. There's non-terminal symbols in here, which keep on being expanded, and there's terminal symbols, which are not being expanded further. So you may have seen such grammars as part of your compiler 101 courses, because they're heavily used for parsing. But what is less known outside of theoretical computer science and fuzzing actually, is how they can be also used as producers. So if you have a grammar like this, what you can do is you can use it to create arbitrary numbers of valid syntactic inputs. So you go and start with a start symbol, which is up here. So let's take the start symbol. And then for every symbol, you look up one of the possible expansions and replace that symbol by the expanded symbol. So start just has become expression. Expression, if you have multiple alternatives, you randomly choose one. Expression becomes term minus expression. A term becomes a factor. Factor can become int.int. Integer can become a digit, and the other integer can also become a digit. And let's choose one digit expansion, and this becomes 8. Let's choose another one, this becomes 2. And for the other expression on the right-hand side, we keep on doing this a couple of, let's make this a few dozen times. And then you actually get this very, very long expression that we have seen initially. And this is exactly the expression that you now can happily feed into the interpreter of your choice. And this is actually a valid input, and this valid input is then being processed by your interpreter. So this of course is a very general idea. And but still, it's not very difficult to implement. So let me show you how this works in real life with a demo. So a couple of colleagues and myself, we have written a book. Sorry, this was too long. Here we go again. So we have written a book called the Fuzzing book, and you can actually look this up at fuzzingbook.org, where we're actually bringing together lots and lots of different fuzzing techniques. And since we are good scientists, we also try to go for the foundations of these things. So let me make this a bit bigger here, such that you can actually see things well. Here we go. And this is the menu. These are all the chapters in here. I can't believe I actually did all that. And if you learn, there's lexical fuzzing, which is these 5 lines of code which produce you all of these inputs. And if you go into syntactical fuzzing, you'll find a chapter here on fuzzing with grammars. And if you go through this chapter on fuzzing with grammars, this is actually all live here and here, you will actually see an introduction on how grammars work, and you'll actually see the very same grammar as it is in here. And then we're going to go to code, and I'm going to show you how this actually works in real life. All of these chapters in this book are actually Jupyter notebooks, which you actually can open right within your browser and toy with them, which I'm doing right here. So now I have reopened the very same chapter as a Jupyter notebook. And now I can go through the same chapter again. The colors are different, but that's about it. And now I can go through these individual parts here and actually execute these code fragments here. So this is the definition for the expression grammar. Actually, I can also make this a bit bigger. Let's see. Oh, this is a bit really big. Okay, let's do it this way. So you have an expression grammar here, and here you see we have a start symbol that gets expanded into expression. The expression gets term plus expression and so on. So this is a Python representation of the grammar we have just seen. And I can also extract individual rules or check whether individual elements are in here. And now I can go and actually very easily go through this thing and define a grammar fuzzer that will happily expand any text you give to it. And now this is not 5 lines of code, but 20 lines of code. Still, it just so fits on a screen. So really grammar fuzzing is not complicated. And now you can go and generate, these are actually the same expansions as we've seen before. I can generate a string that actually is a valid arithmetic expression. And I can also create many more of these. So here we go. And these are, yep, pretty complex arithmetic expressions that are likely going to cover every single, every single feature that your interpreter has. Minus, minus, plus, minus, 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 plus, plus, minus 4, for instance, whatever this is going to end in with. And of course, this is a great, of course, the ability to produce such big valid inputs are very popular, in particular for compiler testing. And this is actually something that we have done a couple of years ago. So you take a grammar, you put it into a fuzzer, and the fuzzer will happily then test an interpreter or compiler or anything you feed it into. And more precisely, we did this with a JavaScript grammar. This was a student of mine. This is now 7 years ago. And he built a fuzzer called the LangFuzz fuzzer for language fuzzer. And he has thrown this into the JavaScript interpreters of Firefox, Chrome, and Microsoft Edge at the time. Yeah, it's still Edge, you know? And so he has generated plenty of JavaScript programs this way. And not very surprising, he actually found bugs in all three of these browsers. Actually, he found many of these bugs. In the first 4 weeks, he netted more than $50,000 in bug bounties. That was great for a master's thesis. And since then, whenever I'm pointing out, you can do, dear students, you can do a bachelor's or master's thesis with me. I always point out this example, and yes, you can make $50,000 in 4 weeks. That's great. This is going to pay for your, for all your year of studies. And sometimes students also ask me, what has this guy earned after the first 4 weeks? Well, it's very simple. He got hired by Mozilla. And as a side job, he still does testing for Chrome and then therefore also for Microsoft. So he still rakes in bug bounties, and he still has found more than 2,600 serious vulnerabilities so far. So this is fun, okay? And this LangFuzz is pretty much the standard still for testing the JavaScript interpreters of these things. So they have entire computing centers running nothing but LangFuzz all day long. And if you use any browser right now for anything on your mobile, or if you look at Zoom through your browser right now, chances are that this will be with a browser that has been seriously tested by grammar-based fuzzing. So that's the fun of it. So this is just a short introduction on creating inputs with grammars, but there's a catch there. And the catch is that if you want to fuzz with grammars, well, you need a grammar in the first place. And while we typically assume that software developers do like nothing more than specifying and modeling, the other half of our software engineering community knows that this is actually a very hopeful assumption. And indeed, my personal opinion is that developers do not like to model. They do not like to write specifications. They couldn't kill us. If only they did, I think everything would be a much better place. But so far, we have to assume that this is not the case. So what we have done in the past couple of years is we have invested in techniques that actually allow you to mine such grammars. And mining such grammars means that you actually do have a piece of code that parses an input and processes it and works with it. And from this piece of code, we want to be able to extract the original grammar that represents it. So how does this work? The interesting thing is the large majority of parsers these days are actually recursive descent parsers and handwritten parsers. This is amazing. I never thought that, but despite everything you might have heard on compiler generators and everything, the large majority of parsers is still handwritten. Even the parsers of GCC and Clang, for instance, they're all handwritten. I don't know why, because they are. And this means that, we actually have a structure in our programs that we can exploit for extracting grammars out of them. So the general idea here is that you do have a correspondence between individual parts of a parser and actually parts of the grammar. And the general idea here is that we dynamically track individual characters on where they are being processed. And this allows us to tell where individual characters, and this allows us to establish a correspondence between characters and code locations. Because what we check is for each and every character dynamically, we check where it is last accessed. And this is a mapping that we then use for recreating the grammar. So in this example, for instance, the character plus is last accessed in this method parse expression. So this is what we do for every single input character dynamically while the program executes. We use dynamic tainting for that. So if we have an input, say like 1 times 8 minus 5, we can assign a particular location, say a function, to each and every character. Say parse digit 1, 8, and 5 are last processed, are consumed in a method called parse digit, and minuses in parse expression. The parentheses are being processed in a method called parse factor. We have parse term in here, and let me rearrange these things a bit such that they look more like a tree, because a tree is what we're going to get out of this. In particular, if we not only create a mapping between the individual characters and the functions in which they are consumed, but we also take into account the call tree of these individual functions, then what we get is a tree that looks like this, which means that we now do have, we also have a hierarchy now. Parse term up here calls parse factor. Parse factor calls parse expression, and so on. And if we add the other methods in here that do not consume anything but simply call the next one, this is what we get. And this is already very close to what you call a parse tree or a derivation tree. A parse tree when parsing and a derivation tree when producing. And you can now go and replace these parse identifiers with actual names, with actual nouns. We do so by extracting the nouns from the method names. This is actually extremely successful. And now from these parse trees, we have multiple of these parse trees, we can now find out that apparently there was a term which got expanded into a term times a factor. So we take this term symbol and it becomes term, and this becomes a times, and this becomes a factor. Obviously, the grammar must have such an expansion because otherwise it wouldn't have such a derivation tree in here. And we take the next parse tree. Here we have term and factor. Well, obviously a term can also become a factor in here. So this is what we get. Factor can expand into a parenthesis and an expression and another parenthesis. And here we go. We have another rule, a factor, but a factor can also be an integer, apparently. And if we repeat this, this is the grammar that we get out. And this is a grammar which actually represents the structure of the input, of the one single input that we have seen so far. And now if we pipe in more inputs into that, then we get another parse tree, and then the grammar becomes a bit more complete. And if we add a third one, there we go. Here we go, say we still need some plus and minus in here, and then we also get the individual parts. And now we have the grammar as we already specified it, but now we have mined this grammar entirely from the processing program together with a set of inputs. And this of course is fun, because if you can do this, then you can now pipe the extracted grammar right away into a fuzzer, and then happily produce plenty of valid inputs from it. So we have built a tool called Mimit, a grammar miner. This is actually my super duper postdoc called Rahul Gopinath. He's on the market next year, so be sure to hire him. And we have this wonderful paper at ESEC FSC later this year, but it's already available as a preprint. So you can look up my Twitter stream for that. So this is Mimit, and Mimit takes a C or a Python program and a series of inputs, and then it produces an input grammar. And this input grammar can go into a fuzzer, you can also create a parser out of it, which is actually pretty useful, because then you can parse inputs and recombine them for search-based approaches, evolutionary fuzzing, whatsoever. And it can also go to humans. What does it mean? It can also go to humans? Well, simple thing. These grammars are actually pretty well structured and pretty readable. So this is a grammar for JSON, which we extracted from microjson.py. This is a Python parser for JSON. And if you ever wondered what a JSON is, well, a JSON is either a string, or it is a list, or it's a dictionary, or it's a number, or it's true or false or null. What is a string? Well, a string starts with a double quote, and then there's arbitrary elements of individual characters followed by another double quote. What is a list? A list starts with an opening bracket, and then either you can have a closing bracket, or you can have an arbitrary number of individual raw elements separated by commas. This is the raw output of Mimit. And this is something that you as a human, well, this is almost textbook quality. The only thing you'd have to do is take this square bracket and put it down here, arguably. Rahul and I disagree where this opening bracket should belong, because because this reflects how the parser works, whereas I'm reflecting how a human would work. But this is just a small switch. And the fun thing is that you as a human, you can now take this grammar and actually modify it to your will. Because one thing you can do with this is, well, for instance, you can add probabilities. Suppose you want to have plenty of dictionaries, and you want to have only just a few lists. Well, you can add probabilities to it, and oops, you're going to get plenty of dictionaries. This is probabilistic grammars, and this is probabilistic grammar fuzzing. All you need to do is, when expanding, you need to take care of the weights respectively. Something else you can do, and this is something which my colleagues at my center like a lot, because they're all working in security, is you can come up with your own stuff. You can actually come up with your own strings and special strings, such as this one, for instance. Just add a special string which is called drop table students, something like that. So this is a string, okay? So for those of you not familiar with the term, this is a SQL injection, okay? So we're just trying to add some extra string, which will later be interpreted as a SQL command. This is not something that your average grammar miner or program analysis or whatsoever tool will actually be able to synthesize, because, well, you would have to go through all the layers of, well, in this case, you have to go through all the layers of SQL to find out what the SQL language is and everything. So we're not there yet. But you as a human, you know this, of course. So you can also come up with passwords and other stuff. But this is particularly fun because if you add something like this into your grammar, what you're going to get if you pipe this into a fuzzer is an input like this. So the fuzzer is going to produce inputs. And here you go. And then it's drop table students, drop table students, drop table students, drop table students everywhere in all sorts of places. And at this point, I'd very much to point out that you should not try this at your university or anywhere else, because you are likely to get expelled more or less immediately, as actually has happened. But yes, these are extremely powerful tools because and that's the fun of these grammars, they allow you to bring in your own knowledge into that, and you can have lots of fun. Okay, actually don't do drop table students, make that alter grade or something like that. And yeah, well, if you manage to break into one of our systems and change your grade to an A+ or whatsoever, no, we're not going to let you through with this. Okay, so there's plenty of possibilities in here, and if you extend this to binary formats and whatsoever, there's quite some fun in doing that. Okay, and the neat thing is that you can bring in your own knowledge into this, and on top of that, well, you can make usage of all the nice features that grammar-based testing techniques have. You can go for coverage. You can make this. You can integrate a guidance towards code coverage and whatnot. So plenty of possibilities in here. Okay, so this was Fuzzing with Grammars 101 and mining grammars. And now let's go a bit further because, well, we're talking about MOBILESoft, and at MOBILESoft, well, of course, mobile devices somewhere also have textual input. Somewhere in the background, there's networking and whatnot. But let's go a bit further towards what we actually see as user interfaces. And for this purpose, I brought a little toy user interface with me, which is here. This is the Fuzzing Book swag order form. So if you want any Fuzzing Book merchandise, you can have a t-shirt or a rotary drill or whatsoever. You just enter your name and everything in here. And then you can place an order. And if there's 1,000 people ordering t-shirts, then I will happily send them to you after I told you how much they actually cost. This is just a simple form. And in this form, well, yeah, you can fill in your name, you can fill in your email, not super surprising. You can fill in your city, your zip code. So this is Saarbrücken. Saarbrücken has an umlaut character in it, so this is already great for testing. And then you click on place order, and here we go. And we have different ways of interacting with this. We have a selection from a menu. We have a type, we can type into individual fields, and we have buttons to toggle, and we also have a submit button at the very end. And the question now is, how do we express the interaction with this user interface? Well, now coming from this idea of a formal language, where a language is a series of symbols, I can actually come up with my own set of symbols, and I can actually say, hey, how about making a symbol and interaction with this interface? This gives me something like this, where we actually get an interaction. And an interaction now is a series of commands on this. So if we enter Andreas Zeller in here, this is actually a command named fill, where we fill in the name field with Andreas Zeller, and where we fill in the email with my email address and the city again, and where we fill in the zip code. And yeah, and this way we get this nice sequence of interactions up here, which actually represents the same as if I were typing characters into it or sending characters over network stream, except that the language in which I use to describe my interactions here is a bit more complex. So we have individual interactions. I can fill text fields, I can click on buttons, and I can press a submit button. And, but of course, I can also generalize things. In particular, I can say, okay, how about any name in here? Because the name, again, is a textual input. So what I actually can do is I can say, well, my name is Andreas Zeller. For the email, I want to have zeller@acm.org. This is, again, a grammar in which this name, a non-terminal here, gets expanded into Andreas Zeller. That's fine. But now I can also add more to this. For instance, I can come up with an alternative. Let's make this David Lowe. Hello, David. I knew you were watching. And here's David. And this then allows me, of course, to, if I now say I want to produce inputs from this, then I will fill in David Lowe in here, or at least this might be one of the possible expansions in here. So David, very soon you're going to get a very nice Fuzzing book t-shirt. So I'm going to send this over to Singapore. But unfortunately, it's still my email address, so I'm sorry about that. I can also come up with other things. So let's come up and send something to Tel Aviv, for instance. Anybody from Israel in here? No? No? Okay, wave your hands. So Hebrew names are particularly interesting because, well, they are challenging for some of the user interface being written right to left. Here we go. So I can also come up with these. Here's actually the zip code of Tel Aviv in Israel. Here we go. Or one of the zip codes, I assume. Wonderful. Here we go. But I can also come up with, of course, come up with generic rules in here. So I can say a collection of first names and last names, and then I can come up with appropriate rules for expanding these, or just saying any sequence of characters in here. That's fine. And then I'm going to get random names. That is pretty straightforward. Likewise, for email, I can come up with, well, a generic rule for emails. Actually, the language of emails is a pretty complex language. You cannot express the language of emails as a regular language. If you ever tried out to find regular expressions that match emails, that's actually impossible. This is actually context-free language. So having a grammar for that could actually be pretty useful if you thoroughly want to test that your form accepts all the email addresses in the world. Having a grammar for emails could actually be the toughest test you can imagine. And you can also come up with, so what happens now? Yeah, and then of course you also have a random, you can also have random zip codes in here, that's easy too. But you can also come up with invalid values, of course. So I come up with a negative zip code. Here you see negative zip codes. Let's see what happens if we do that. Or just plain stupid, we had this already, just enter drop table students in here, and then your form will be happily filled with drop table students commands all over the place. This is actually where my students, when they do security testing, when they get super excited because they can't wait to fill every single form they find on the web with drop table students commands. And yes, the very first instantiation of our new student course management system was deployed in computer science without having been properly tested. And yes, it took our students less than 10 minutes to find a couple of very interesting SQL injections. Then the university wanted to sue them, but then fortunately we told them that this was not the way to go, and now we gave some extra points to these students for properly applying such such techniques in practice. Okay, just forget about drop table students. Make that add table canary or create table MOBILESoft or something. Okay, don't do this at home. Okay, so this is a neat thing again, because if you can extract, if you have such a grammar, you get full control over the text being entered, and you get all the features of text-based fuzzing, and you actually get a nice integration of GUI fuzzing or fuzzing with graphical user interfaces, as well as putting in text in here, because, well, we can also combine this with inputs of other sources. So if you want to, you can also say, okay, I have a network event coming in at this point, or some interaction with other stuff. It all depends on the actual events that you model in your specific language in here. And you can also mine these. Actually, you can also, rather than producing inputs from these, you can also take an existing interface and extract these, which is not very complicated. Because all you need is you take a look at in this case, this is web form. You take a look at the HTML tags, and then you take a look at the HTML tags, and then you go and extract the appropriate input fields. So you know that name already is a string, and email, actually this is an email field. And then you can actually get these grammars out of an existing user interface automatically. So this is and of course, if your form already has appropriate accessibility features telling that an email field actually accepts an email, there's an HTML, is it 4 or 5 standard for this? Then this is of course also something your grammar will be able to reflect. So I'm having a demo time in here, and this could actually be fun. Let me see whether this is going to work. So I'm going to switch over to another chapter in the Fuzzing book, which is aptly named Testing Graphical User Interfaces. And this is also something you can do at home, actually right now if you wish. I already have started this thing. So this is a chapter which uses Selenium to remote control a web browser via user interface. The chapter is fully self-contained, so it comes with a web server as well. It doesn't come with a browser. It comes with a server, and you can actually run everything right within your browser yourself. This is fun. And at this point, we are in a situation where we already have this server running up here. So I can actually enter text in here just for the fun of it. Here we go. And since this is controlled by Selenium, I have plenty of control, which you can exercise right within my notebook here. For instance, I can go and get a screenshot. Well, is this really the screenshot? Well, let me put in David up here again. Hello, David. Or, well, Leonardo. Leonardo, ¿cómo stai? Let's see. And I do a screenshot in here. And, oops, where's my screenshot? Ah, here we go. You see that the screenshot which I got also has the name Leonardo in it. Also, this is fun. So you can actually, so this is really cool. I mean, you're in this interactive environment here, and you can now go and happily remote control your browser, and of course also write functions that work with it. So I can actually access individual fields in here, and I can send strings in here. And if I change this, say to Leopoldo, hello Leopoldo, then it's going to be, oh, Jane Doe Leopoldo. Maybe that's a bit too much. Let's delete this thing. And let's send Leopoldo again. Wow, cool. How cool is that? So if you ever want to teach your students how such remote control works and an interactive stuff, I mean, the normal thing is you have this big Java program, whatsoever, you build this huge Java infrastructure, then you press a button, and then somewhere in the background, there's a server running, but you never see it or anything. I can tell you, this is more fun just looking at stuff in here. So, you can actually fill this, you can actually now go and fill this out. Let's send a Fuzzing book t-shirt to Leopoldo here. And then now we can also fill in the individual parts and again take a screenshot, and it is Leopoldo. How cool is that? And you can even click on individual elements. There you go, you click and then you submit this thing. And as you can see up here, this is now being ordered to Leopoldo in Seattle. Leopoldo, you come from Seattle? No, probably not, right? No Leopoldo from Seattle. Okay, good.
Recife.
Sorry?
Recife, Brazil.
Okay, here we go. Okay, and so this of course allows you now to fill out stuff as you like. And yeah, if you take a grammar and fill out stuff as you like, well, you can have lots of fun. You can have lots of fun actually filling out these forms, including with stuff, say like drop table students and whatnot. Okay, so this is all fine. This is all fine too. Here we go, here we go, here we go. Yes, okay, good. So this was just a bit of how Selenium works if you work in an interactive style. And now let's go make this thing a bit more complicated. Because normally you do not simply have a single form to be filled out. So that's already pretty straightforward. But instead you actually have a whole user interface consisting of several screens or windows or activities or however you may name them that are connected to each other, and you can navigate between these. And the question is now, how do you represent not only a single form, okay, with its clicks and text inputs, but how do you represent such entire structures of things? Well, the common way to do this actually is that you do have a user interface model for this. And the classical way for this is that you do have that each screen in there becomes a state, and you have transitions between these states, transitions that are being actionated by clicking on the respective user interface models. And this gives you a very nice finite state model. So from the order form, you can submit place order, and then it gets thank you for your order. You can also go back from either of these by clicking on the order form or by going back. And, and since this is a finite state automaton, you also need some start state in which you start. And then you can go and then you can happily go and navigate through these things. And of course, such models are super nice because they allow you to tell how many states have I actually covered, how many transitions have I actually covered. And when you do tests of such user interfaces, you also want to cover all the individual transitions in there. And this is all neat and nice. But there's one problem though, because then the problem is in this part, this fill part. How do you specify those inputs that need to be generated? So how do you bring in textual inputs in here? So this makes life a bit, so you have the choice here. So we have these nice textual grammars for representing what textual input should be. And we have these finite state models representing what states exist in our system. Now you can come up with all sorts of mappings between the two, or say, okay, I'm having a special grammar here for this filling or whatsoever. However, it turns out that you can actually put both together, because what you can do is you can go and translate this finite state model, which actually is a sequence of interactions. Okay, you start up here, you go down here, you go up here, you go down here. This is a sequence of interactions. This is a language of interactions, a string of commands. Well, you can do the very same with a grammar. And this is actually, a grammar is actually the more powerful representation, because you can actually embed such a finite state automaton into a grammar. How does this look like? Well, as always, you start with a start symbol. And when you start, you end up in the order form. So you actually see that these states that we have in the finite state machine now all of a sudden become non-terminals in our grammar. And you can do the same with the order form. And from the order form, well, you can click on terms and conditions, and then you end up in a new state, which is terms and conditions. This is one alternative. The other alternative is that you can also fill in the form and then submit on click on place order. And then you're going to end up in the state, thank you. And if you're in terms and conditions, you can click on order form and you end up in order form. And if you have thank you, you can click on order form and you end up back in the order form. They're not very surprising, all this. And the cool thing is that both of these, the finite state model up here and the grammar down here, actually represent exactly the same language. So you can actually automatically transform one into the other. You can also take this grammar and visualize it as a finite state automaton. This doesn't make it, this is just the same. This is just another representation, if you wish. However, having this as a grammar has one very neat advantage. And this advantage is, again, when we look into how do we specify those inputs to be generated. And this is actually now a problem which is down here in this fill. Well, in this representation, we do have a grammar, and we can actually fill this out because we can actually say what is to be filled. So we can say, fill in a name, fill in email, fill in city, zip, boolean, whatsoever. And now what we do have is a hybrid model that has parts of the finite state machine, which is all these states in here, yet also allows us to express all the textual input that should take place in here. And this is something we can easily put in here. And yep, also including drop table students and whatever SQL injection command you may wish to apply. And yeah, I'll say this is Ibn al-Hazan, for instance, inventor of the scientific method. We can add a value in here. Email, well, drop table students, well, okay. Actually, if you put in drop table students in an email field, it may not be recognized as valid, so maybe this is not going to work well. Okay, another neat thing is that there's algorithms for grammar-based testing that actually go and say, you should actually explore each and every alternative there is in your grammar. Because your grammar alternatives represent alternatives in the input, which again represent alternatives in behavior. And this means that, and this has an interesting effect, because if you go through all the alternatives in the grammar, you're also going to cover everything there is in your model. And for instance, over here, we start with an order form. Well, we have that covered. That's not very complex. This means that we just have covered this transition over here. And now we go for the terms and conditions, and we have covered the transitions to terms and conditions. If we are in terms and conditions and go back to the order form, we're going to cover this transition up here. And if we now go for the next alternative, which is an alternative in name, alternative in email, well, filling these out, we're going to cover this transition. Going back from thank you to the order form, we're going to cover this other transition. But we're not only covering those transitions, we're also covering all the different alternatives, all the different alternatives and names in here. So, because in the end, we're also going to cover this drop table students thing in here. So actually, this allows us to have a single representation and one single algorithm that's going to give us all the states and all the transitions and all the textual alternatives. And if you actually expand this somewhat, you can even come up with all combinations of all of these. Of course, all combinations of all states and all transitions and all different expansions of names. This is going to end up this is going to come up with an exponential, with a combinatorial explosion. But for this, we have plenty of algorithms that tell you, well, it suffices that you cover every transition. It suffices that you cover every alternative or every sequence of transitions or every sequence of alternatives. This is all set in the beautiful field of model-based testing, which you get for free here when you do this with grammars. So UI grammars can also be used for parsing, by the way, them being grammars. That's actually neat, which allows you to parse sequences of interactions and recombine them. Great for search-based testing. You can encode multiple input sources, network inputs, intents, OS interaction, and they can be represented as a visual finite state model, just in case you prefer diagrams over text. And for this, I'd also like to give you a demo on that. So let's get back to our fuzzing book thingy running up here. So let's see where we are. So we got this nice little image and we can do all that. So let me proceed a bit further through this thingy here. just to be sure that we don't skip things. So just bear with me for a second. Here we have something for mining the grammar and everything. Yes, that's all fine and neat and all together. And here comes the interesting part, because we can actually go, and this actually explains how to extract such state machines from a system. And I'm not going to give you through all the code there is in here, but instead I'm going to get you through the actual result. This is already a grammar, which now is represented as a finite state machine, because we have a nice way of converting these grammars into state machines. So you have a start, you have a state in which you start. You can click on terms and conditions. You can fill, check, fill, submit. You end up in another state, which is yet unexplored. And we can now go and proceed further through our code in here, which actually allows us to run all this stuff. And while we are doing this, look at the window up here where it's actually running and changing. And what our system here is actually doing at this point, it's actually exploring the entire site and looking at all the interactions there are and completing its state model, and at the same time also completing its grammar. So now here we go, and now it's filling out things one after the other. And at this point, yes, it's actually running autonomously and already has extracted, here we go. And at this point, it has explored the entire grammar. So this is the grammar with all the different states and all the different ways of interacting with it, which again, you can see as a finite state diagram. So now we have, so this is, I apologize for the very tiny screen here, but we do have the original state. This is the order form. From the order form, you can go into this field of the order form is accepted. And from there, you can click on the order form in order to get back to your original state. Here you have the second state, which is terms and conditions. And from any of these, you can actually go and end the interaction such that there actually is also a final part in it. Just because it's so much fun, here's the grammar. This is the grammar again. And again, here's the finite state diagram. How nice. And you can now take individual rules up here. For instance, a string in that grammar expands into character, or a string followed by a grammar. Yeah, and now you can alter the grammar again to insert your own commands into it, such as drop table students. And now your grammar has the expansion of drop table students. And if you run this, well, sorry, can we do this again? If you run this, you will happily now fill things. Oh, and here we have it already. Send the Fuzzing book t-shirt to drop table students in drop table students, 5. Well, let's make this a bit bigger. Here we go. Wonderful. So now we already have a mechanism. When you run these grammars, you will have drop table students all over the place. And actually, if you look at the background, so this is, if you look into what's happening in the background, there actually, in this web server, there actually is a SQL command, and actually is a SQL database attached to it in the background. And if it weren't drop table students, but if it were drop table commands, you'd actually get it to break. I've deliberately written this to be super vulnerable, both with known vulnerabilities as well as unknown vulnerabilities. And yes, you can run all this stuff at home, which is probably to be preferred over trying this out on a server of your choice. So this was the bit about using such grammars, extracting them and toying with them. So and yes, this is all there for in a textbook form, which you can try out yourself. But I'm very happy to point out we also have implemented this for real systems. So we have implemented this for Android under the name DroidGram. If you Google DroidGram, you're going to find that. And this actually does the very same steps as I just illustrated for Android. We have a test generator to obtain initial seeds. And then this actually extracts such finite state models together with descriptions of the entire input and everything. And this is also something that we have happily tested. So we tested this on 46 apps from Android, and we find that such UI grammars, they cover transitions and code faster and with fewer inputs, because because you have a good model underneath. And if you have a good model, you always know the quickest path to some particular expansion or to some particular state. And of course, once you have such a grammar, you can combine it with arbitrary techniques for grammar-based testing. You can combine it with symbolic execution and whatever you like. So this is a neat tool. And in the GitHub page, you will find both the code for it, but we also have a journal version of that paper currently in preparation. So this was a bit about user interfaces, and let me close with perspectives on things. So where are we going from here? So initially, this was the slide which I showed in the beginning. This was a call for modularity, and we have so many tools right now which put everything together in one single place. We have tools that go, oh yes, you give it an Android program and you give an Android app, and then they will magically click through and they will magically determine what to do next. And then they will magically do the right thing. This is all neat. But if there's something which I want to learn from this, I want to decompose things. And with an approach which I just showed you, well, of course, I invented this for a textbook, obviously, okay? So, and if I have, if I want to show students how things work, I cannot go and show them the whatever 100,000 lines of my favorite Android test generator. But I maintain that it's useful if you do have such a separation. That is, if you do have a separation that allows you to extract models from user interface in the first place, and this is one approach. Second approach is take these models and use it as a parser, use it as a producer. There's a second step. And if you have these on top of these, then you can go and build your testing and exploration strategies with all the knowledge you need. And this is something which our community, in particular, being a scientific community that is interested in figuring out not only how whole tools work, but actually what the individual components are. This is something our community should pursue as a scientific discipline. And as a software engineering discipline, even more, we should be very interested in modularizing our tools, because right now, when I just finished my reviews for ASE, and yes, there's nice magical tools where they throw everything in under the bus, and where they add this magical algorithm, and then they throw in a kernel extension, and then they make this work under their own handwritten Android variant, whatever thingy. There's 500,000 ingredients, and in the end, it's 5% faster whatsoever. But I have no idea ever which of these actually helped, and there's nothing to be learned from that, except that I now have a tool which is 5% faster at the expense of whatever technical depth, which is also a software engineering term. So we should think about how to, well, we have written these tools now let's try to understand what actually makes them. And this is where such modularity is important. At the same time, I should point out that we are still at the very beginning of things, because grammars represent context-free languages, that's fine, but there's also context-sensitive languages, as anyone in programming languages knows, of course. You have identifiers that are being reused all over the place. You also have universal languages, which is wonderful because they're Turing complete, and which is awful because they're Turing complete. So you get everything as you like. And we have seen how to apply these for testing, but there's also nice applications for debugging, for instance, because having such language also allow you to decompose inputs and find out which parts of the inputs are actually relevant for a particular behavior, say a failure, for instance. You can very easily decompose these. You can also use them for prevention, for instance, to find out, oh, there's a specific sequence of interactions which causes my system to crash. How can I prevent this from happening? Can I come up with some protection device for that? This is something which is very easily realized if you have a good parser for it, but still there's plenty of things to be done. And well, we have batch systems that take our input, say a compiler, and then work with it. Stateful systems, interactive systems, reactive systems, where the whole notion of state sometimes is very difficult to catch and which needs to be modeled. And also we have individual functions in our systems which actually have their own sets of inputs or languages to be worked with, where there's correspondence in here. Well, what language theory, in formal languages, a set of inputs is called a language. In programming language, a set of inputs is called a type. What's the correspondence between types and languages and sub-languages? There's zillions of things. There's zillions of things that these interactions still to be learned. And this was a bit on perspectives, and I think I'm totally running out of time, so let me close things here. This was user interface grammars, keynote for MOBILESoft 2020. And what is it that we've seen? We've seen how to mine grammars. That is, take in a program and automatically extract its input language, which we can use for fuzzers, humans, and parsers. I've shown you how to express interactions as grammars, as sequences of interactions, even with graphical user interfaces. I've shown you how to embed state models into a grammar using a correspondence between classic states and allowing to integrate both user interface interaction as well as textual interaction, as well as transitions between states into a single model. And finally, a call for modularity, both for us as scientists as well as software engineers. And if you're interested in any of these, follow me on Twitter. It's on Andreas Zeller. And you can also look up the slides for this talk in the description of the keynote as well. If you go into the chat window right now, you'll be able to retrieve them as well. That was it. Thank you very much. And I'm happy to take questions. Thank you.